Welcome to today's Explainer. We're unpacking a massive, kind of hilarious contradiction in modern tech right now. We live in a world where AI can write completely functional software, compose poetry, and literally pass the bar exam in a few seconds. But ask a robot to reliably clean your kitchen without causing a total disaster? Yeah, we hit a massive wall. There's this wild, stark contrast between the rapid evolution of digital AI, the chatbots we use every single day, and the surprisingly slow progress of physical robots actually trying to navigate our messy, real world.
Let's dive right into this by framing the actual stakes here, because they are huge. Think about it. If you ask a large language model a question, and it takes 2 seconds, or even 2 minutes, to spit out an answer, it's really just a mild annoyance, right? Nobody's getting hurt. But what happens if you apply that exact same processing delay to the physical world? Imagine a self-driving car traveling at highway speeds. A 2-second delay in seeing an obstacle, predicting a crash, and deciding to hit the brakes? That's no longer an annoyance. That is the literal definition of life or death. The AI we have today is just fundamentally unequipped for these split-second, high-stakes physical decisions, especially under strict power limits. We need a completely new architecture.
Which brings us to Section 1. Enter the world model, moving AI into the physical realm.
So a world model completely redefines what AI is actually doing. Look, a language model just predicts the next token or word in a sequence. A world model, it has a significantly harder assignment. It's an AI system explicitly designed to watch live video, listen to audio, maintain a persistent memory of a three-dimensional space, simulate the actual laws of physics, predict the consequences of its physical actions, and do literally all of that continuously in real time. It's not predicting the next word, it is predicting the physical world itself.
To picture this, imagine a robot standing in a kitchen. It sees a cup on the counter. Suddenly, a person walks right in front of the camera, completely blocking the cup. Instantly, the robot has to execute what we can call the robot loop. First, it has to remember the layout of the room and know that the cup still exists behind that person. Second, it has to predict how that person's going to move and understand that the counter is solid so the cup won't just magically fall through it. Third, it considers its own actions, like what happens if I reach to the left? What if the person steps back? And finally, it executes an action and then instantly repeats this entire loop, over and over. It has to run this loop dozens of times every single second, all without losing track of what happened, say, 5 minutes ago. And to pull that off, you need serious computing power. And that takes us to Section 2, the AI data traffic jam, why we can't just add more chips.
Just look at the sheer volume of data the physical world produces compared to the digital world. 1 minute of ordinary spoken text written down is usually less than 1 kilobyte, tiny. But 1 minute of raw, uncompressed 1080p color video at 30 frames per second, that is roughly 11 gigabytes. The video is literally 10 million times larger in size. 10 million! And that's before you even factor in audio, spatial depth, or a robot's own joint positions. The physical world creates just a ridiculous amount of information, and our current chips are totally choking on it. It helps to think of an AI chip kind of like a city. You've got the factories. These are the arithmetic units doing all the heavy math. And then you have the warehouses and roads, which represent memory storage and data connections. Now, here's the absolute crucial point. You can build as many new factories as you want. You can double your compute power. But if every truck is stuck in traffic on those roads and the warehouses are completely jam-packed, production doesn't double. You just end up with a bunch of highly expensive machinery sitting there twiddling its thumbs, waiting for data. Moving data, not doing math, is now the central constraint.
Because of this massive constraint, the biggest tech companies are frantically trying to figure out the most efficient way to build a world model. And honestly, there's absolutely no consensus yet. Google DeepMind's Genie 3 is a generative model that actually creates a fully interactive 720p environment. Meta, on the other hand, is taking a totally different route with VGPA 2. Instead of processing every single pixel, it predicts using compressed internal summaries called embeddings, completely ignoring useless details like, say, the glare on a countertop. Meanwhile, NVIDIA's Cosmo 3 tries to combine language, image, video, and audio using a mix of prediction and diffusion. What this really tells us is that the industry hasn't even agreed on the basic unit of intelligence yet. Should the AI process raw pixels, recognized objects, or compress summaries? And until they decide on that, we really can't build the perfect hardware to run it.
Moving on to Section 3, the hardware divide. One model, two entirely different machines. See, running a world model effectively isn't going to take one massive supercomputer. It actually takes two completely different machines.
On one side, you have the data center, like NVIDIA's Rubin chip. Its job is training the AI and running millions of simulations. It is an absolute monster with 288 gigabytes of ultra-fast memory, moving data at an astonishing 22 terabytes per second, with practically unlimited power at its disposal. But then, on the other side, you have the edge device, the chip that's actually sitting inside the robot or the car, like NVIDIA's Jetson Thor. Its job is real-time action. It has to survive on just 40 to 130 watts, run on a battery, and avoid literally cooking itself to death. So the training chip requires extreme memory bandwidth, while the inference chip requires extreme efficiency.
But hardware isn't the only way to solve this, thankfully. Software innovations can actually help erase these massive hardware demands. Take Microsoft Mirage as a great example. Instead of constantly rebuilding a room in its memory from scratch, frame by frame, Mirage stores the static, unmoving parts of a scene as 3D tokens. It only updates the things that actually change. By remembering spaces way more efficiently, researchers achieve 10 times faster generation using 55 times less cache memory. It's this exact kind of software breakthrough that will allow these crazy power-hungry models to eventually fit inside a walking, untethered robot.
All right, Section 4. Who wins the race? The economic battle for physical AI.
Make no mistake, solving this bottleneck is a multi-trillion-dollar economic battle. And we can break the likely winners down into 4 distinct groups in the ecosystem. First up, you have the full-stack incumbents, like NVIDIA. They make the adaptable, general-purpose chips that researchers desperately need right now while they figure out the best architecture. Second, you have the vertically integrated giants. Tesla is a prime example here, co-designing their full self-driving software, their custom AI chips, their cameras, and their Optimus robots all as one single cohesive product. Third, we have the memory and packaging suppliers. Since data movement is the main bottleneck, companies like Samsung, SK Hynix, Micron, and TSMC stand to profit massively regardless of which software model actually wins out. And finally, definitely keep an eye on startups like Cerebras, who are completely rethinking chip design by building massive pizza box-sized wafer-scale chips just to keep compute and memory as close together as physically possible.
So how do we know when we've actually arrived at this sci-fi future? Well, here is your physical AI cheat sheet. These are the exact metrics you should be tracking. Watch the cost to generate just one single second of a consistent interactive world. Watch how long an AI model can remember a physical place before its compute needs absolutely explode. Watch the power consumption required for a robot to perceive and act in real time. Watch closely to see if the industry settles on pixels or compressed objects as the standard unit of intelligence. And maybe most importantly, watch for a system that proves successful not just in a beautifully rendered video simulation, but for hours on end inside a real physical machine out in the messy, real world. When you look at the sheer scale of these hardware bottlenecks and the massive compute requirements we've dug into today, it can honestly sometimes feel like we're reaching the end of AI's rapid development curve. But think about the absurd economic potential waiting on the other side of this bottleneck. We're talking about self-driving cars that operate flawlessly for years, and humanoid robots that can execute literally any physical task faster, better, and cheaper than we can. The shift from language models to world models isn't the end of the line. It fundamentally changes how machines interact with our reality. So, are we hitting a wall, or are we really just getting started? I'll let you decide. Thanks for joining today's Explainer, and keep your eyes on the physical world.